Look at that.
Wonderful. Thank you.
Hi, I'm Mike Paluszek from Princeton Satellite Systems, and I'm going to be talking to you about nuclear fusion propulsion. So, what does this do for us in space? Why do we need it? Well, it solves three problems we have, and this relates to science. One is power. How much power do you have to do the things you want to do? The second thing is, how long does it take you to do what you want to do? And the third thing is, how do you get the information? This is all relevant to science. You do a great experiment, you come up with a payload for a spacecraft, you launch it, 10 years later it gets to its destination, and then you get data back at 10 bits a second, and that inhibits your ability to do science. So the first thing is power. Now, how do we get power in space right now? Well, there are kind of two ways of doing it. One is RTGs, which are little plutonium radioisotope generators, and they produce very little power, but they can do it anywhere in the solar system. So spacecraft like New Horizons use them. Other spacecraft, and this is the vast majority, use solar panels. Now what I've done is shown a picture of the space station with a 1 megawatt array on it. People are talking about this size array for, say, solar electric tugs to go to Mars. You see the size, and besides the cost and the complexity, you have a lot of control problem with something that big. So time is, how long does it take you to get there? Now look at New Horizons, a fantastically successful mission. It took 9 years to get to Pluto. It was very limited when you could launch it because you had to launch it at a time where you could get swing-bys from the big planets. That constrains when you can do your science. And one of the fundamental problems that you have when you go to electric propulsion, which might use the big solar panels, is a quantity called specific power. It's the ratio of power to mass. This limits you to what you can do with electric propulsion, how fast you can go, how soon you can get places. And it's a critical limit. People, being very optimistic, think you might get 0.2 kilowatts per kilogram from solar, maybe. With fission, it's more like 0.02. So that constrains what you can do with any of these power sources. Communications is pretty simple. I wrote the whole equation down. But fundamentally, it's proportional to power. The more power you have, the higher your bandwidth. So New Horizons is sending back data very slowly because it has about 200 watts, maybe 100 watts dedicated to communications. This means that even if you can do great science, you don't get much information back. So we want more power for that reason too. So now I'm going to talk about what we call direct fusion drive. It is a fusion technology particularly suitable for rocket propulsion. It can also be used for terrestrial applications. So this is a very busy slide. I'm not going to read the whole thing. That's a picture of our experiment. It's being run right now at the Princeton Plasma Physics Lab down in Plainsboro, New Jersey. You should all come and visit and see the experiment in operation. There are a couple of things that are important in it. One is that it has a very high ratio of plasma pressure to magnetic field pressure. This is called beta. A tokamak is about 0.02. We're close to 1. That means you can use much smaller superconductor coils, much lower fields, and much less massive superconducting coils for the same amount of fusion power. It's very important for space, getting back to our specific power number. If you have really heavy coils, your specific power goes down, and that's bad. Another really important thing, and this is something you don't hear about even with the big tokamaks like ITER being built, fantastic technology, is neutron load. Now if you use deuterium-tritium, most of your power is in neutrons that bombard your inner wall, which lasts about 3 months. And there are a lot of problems with that. For a spacecraft, obviously we can't go 3 months, we need to go years. So what we've done is switch to a fuel called fuel combination deuterium-helium-3. This reaction by itself produces no neutrons. However, as you can imagine, when you have a big mixture of deuterium ions and helium-3 ions, some of those deuterium ions will collide, producing reactions. Those are called side reactions, and some of those produce neutrons. Nonetheless, we end up with a much lower neutron wall load than with a big DDT machine. Now, the other interesting thing about this is that it has to be very small by the nature of the heating mechanism, which is essentially like an induction motor. This is a driven fusion machine. The ideal for a big tokamak is that you get it up to temperature, and then the products produce all the additional energy needed to keep the fusion reaction going. Now that will not work in practice at all. You're still going to need about 10% of the power coming from the outside for a variety of things you need to do with a tokamak or a stellarator. In our case, all the energy needed to heat up the reactants comes from the drive, which again is like an induction motor. Now the nature of this, because of the ability of the RF, the radio frequencies from this drive to penetrate the plasma, limits us to 10 megawatts, which fortuitously is exactly the size we need for space propulsion and actually for a lot of terrestrial applications. So it becomes direct fusion drive because what we do is we have this internal, what's called a field reverse configuration. It's a closed magnetic geometry. So we have a solenoidal coil, we have mirror coils, and then when we turn on the rotating magnetic field, we get a closed geometry, and we have a flow of plasma in the toroid, and that's where we're getting our fusion from. So you say, well, how do we get thrust? Well, what happens inside that geometry is that the products come out into what's called a scrape-off layer. That's the outside of the closed magnetic field. And we flow additional deuterium or hydrogen ions by that, and that's how we get thrust through a magnetic nozzle. It's very similar to Vasimir, only we have fusion going on inside of it. Now, here's the problem. All the plasma physics is in that very nicely colored box, which says plasma. But we have a lot of other subsystems which are critical to making it work. As I said, it's a driven machine, so you say, well, where do we get the power to drive it? We get it from waste heat. Now, any kind of machine that's operating at this temperature gets a lot of X-rays coming out of it, which is not as much of a problem with a deuterium-tritium machine. It's a big problem with this. It's a bigger problem if you try to go with boron-proton, which other people are trying to do. That has to be captured. We have to capture any synchrotron. That's RF radiation from the motion of particles in the field. That has to be captured. Waste heat from the few neutrons we have hitting the walls, we have to recycle that, and plus any additional just heat flux into the walls. So we recycle that through a Brayton cycle heat engine. Now, Brayton cycles work best when they have very high pressure ratios. That means it's heavy. But the interesting thing is we do need shielding for this machine. And we mentioned shielding in this block diagram. And what we're trying to do is determine if we can integrate the structure, which holds the coils together. Remember, these are coils producing very high magnetic fields, and they want to pull themselves apart and pull themselves together. So we need structure to handle that. We need structure for launch loads, but we also need the shielding because we have to protect our superconducting coils from our few neutrons coming out, and we need the heat engine. So what we're looking at now is if we can integrate the heat engine cooling pipes into this ceramic shielding, so we essentially get all these things for the price of one. So the shielding may become actually a benefit, as it turns out, rather than a detriment. Other things we need to do is you say, well, what happens if your reactor shuts down in space? We need to start it up, but it turns out because this machine is so small, we can actually just use a combustion engine to get it going. We need a few kilograms of oxygen mixed with our deuterium or hydrogen to get it going. That's an important consideration because years ago, NASA was looking at really big tokamaks for space. They looked at a spherical tokamak, and they needed a fission reactor to start it up. So we're much smaller. We can do much simpler things. So you say, well, where are we? Well, this is our program plan. We do not have the funding for this. The good news is that NASA is very interested in it and has given us 3 different grants to work on this. Currently, we're getting really long pulses, 300 milliseconds, which may not seem long to you, but in the world of plasma physics, those are almost forever. When we actually put in our first proposal to DOE, they said, well, what do you need pulses more than 2 milliseconds? You can do all the plasma physics you want 2 milliseconds. But now we're up to 300, and that's really only limited by the fact that our solenoidal coils use induced currents. They aren't driven. The actual machine would have driven currents. We're currently demonstrating really good heating of the electrons, and the next step, when we get the much higher RF power levels, that's the drive, we're going to demonstrate ion heating. So we're at PFRC2. It's in operation now. We operate it every day. You can turn it on in like 15 minutes and get it going. The next goal is to get enough money to build PFRC3. The first part of it, we'd use hydrogen as the gas, so we would not get any kind of fusion. And then eventually we would put deuterium and helium-3 into the machine and actually get fusion. And that's 5 to 7 years away, depending on funding. So, talking about missions, this very comprehensive diagram kind of shows you all the different propulsion systems fit in to the world of space propulsion. And a couple of key equations, pretty much all you really need. One is the power equation, which is, in a chemical engine, the power comes from the combustion. In this case, you have to insert it from electricity. And then you have the relationship between mass flow, thrust, and exhaust velocity. And then there's also the rocket equation, of course. And this shows roughly where an Earth-Mars round trip would be. This shows an asteroid deflection. We've looked at that on many, many missions we've looked at. And here's some example missions. The first paper we did on propulsion was actually for the DARPA 100-year Starship Conference. And our design at the time got us to Alpha Centauri into orbit in 500 to 700 years. Now you look at this and say, well, what about those neutrons hitting your machine? Like, yeah, that would not last 500 years based on current technology. But we have some tricks where we can actually lower the neutron production. So who knows? But 500 years, well, that's a long time, but Voyager's been operating for 40. So we're only an order of magnitude off. Not too bad. We're actually going to give you a paper next week on an improved version of that, so stay tuned. We looked at an L2 tug. We said, gee, suppose instead of taking the James Webb to L2 with a chemical engine, use this. We did that. The Mars round trip was kind of fun. We said, well, what do we do if we can, let's see if we can replicate Apollo 8 going to Mars. So we came up with a mission where we got there in about 150 days, orbited Mars for a few weeks, and then came back to Earth. And that was interesting because we had to came up with kind of a clever trajectory which came inside the Earth's orbit around the sun to get back to Earth more quickly. And asteroid deflection is an important thing that people don't worry about too much, but eventually a big asteroid is going to hit the Earth, and that's going to be it. We actually are, this technology could be used, well, there are other methods of doing it to deflect such an asteroid. So these are different missions we've looked at to try to span possible activities of interest in NASA and people in general. Most recently, we got a NIAC grant to look at a Pluto orbiter, and we were motivated by New Horizons, which has produced tremendous scientific data. It's a fantastic mission, but would it be much better if you went into orbit? So we came up with the idea of using this engine to go to Pluto, go into orbit, and deploy a lander which you power with a laser beam from the spacecraft. Now, because you have 1 megawatt of power from your engine, which you can switch to power generation mode, you can do this kind of thing. And that's an interesting application. This is what it looks like, and if you look at the numbers, if you can see them, those are meters. So it's roughly the size of the Hubble Space Telescope. And both the deuterium and helium-3 tanks are just under the sun shield. We have 2 engines in this case. There's an interesting thing you have to know about this, which most people wouldn't notice, is that we've got a big dipole in there. So in the Earth's magnetic field, you get a huge torque on the spacecraft. So we have to add a compensating dipole, we don't show it here, to cancel that when you're in the Earth's magnetic field. So anytime anybody wants to fly something with a big magnetic dipole, you say, what about that big torque? This gives you the numbers that we put in our NIAC Phase 1 report. NASA's granted us a Phase 2, which is great. And it gives you kind of some of the parameters. It's not that big a spacecraft. You could launch it off an Atlas or a Falcon 9 into low Earth orbit. Now, the mission we're looking at now is of great interest to scientists is putting a spacecraft at the 550 AU point and using the sun as a lens to look at other star systems. If you could do it, that's about what you would see, the picture of the Earth in the upper right-hand side. And the current idea is to put your spacecraft on an SLS, which is about $1.5 billion launch, and then do 1 million flybys and get out there in about 60 years. I think 60 years is right. We can get there in 13 years if we do a flyby, but when you get out to 550 AU, in order to get this picture, you have to scan. You have to move the spacecraft in translation. You can do it if you're flying by, but how much better if you can actually put yourself into solar orbit, and that would take about 18 years based on our latest numbers. So this gives you an idea of what a mission looks like with our system. we actually spiral out of low Earth orbit. It takes about 28 days. We're not in the inner belts for that long. And that cuts your launch costs. Now, one of the things about doing science in space is cost. If you have to launch a mission on an SLS, there's only going to be 2 of those a year if you're lucky. And it's going to be really expensive. But if you can launch it on a Falcon 9, your costs drop dramatically. So we found that the actual amount of fuel needed to spiral out was almost nothing compared to the fuel needed to get there. So again, it makes the whole mission cheaper. And you have to think about cost. People have talked about today, a lot of missions just get canceled because of cost. The Jupiter Icy Moon Orbiter mission, which would have been a fantastic mission, was $16 billion before they started bending metal. It would have been $30 billion by the time they did it. It got canceled. And we don't want that to happen to every scientific objective we have. This is what the spacecraft looks at like. The big tank is liquid deuterium. The smaller tank is gaseous helium-3. There's no reason to keep that cool. This gives you a comparison with New Horizons. Again, New Horizons was a phenomenal mission, but it was limited by its power source. So, the conclusion's that direct fusion drive can enable all sorts of new science and new missions that are very difficult and very expensive to do today. It reduces the complexity of the mission plans. You no longer have to launch at a specific date to do all these flybys, like many missions do. I mean, JPL can do amazing work in doing these flybys, but they take time and money. Remember, 1 year in space costs you about $50 million. That's operations cost. So the faster you get to your destination, the more time you have to spend on science. The sooner you get your science back, and ultimately, the lower the cost of the system. And that's my email address if anybody wants to ask me any more questions after the talk. Thank you.
So we have time for a couple of questions. Yes, please.
So Mike, maybe that help us connect the dots back to the sort of going to private space science theme for the day.
Yes.
Where do you view as the next step in private funding or private collaborations to space science?
Well, we're really fortunate to have NASA giving us money for this mission. But to get to fusion, we need $50 million roughly in about 5 years. And it's very difficult for NASA to do that. And there's nothing wrong with NASA, but there's sort of there's the valley of no funding. And if you have lots of money for little projects, and they have STTRs and SBIRs, which we're being funded through, for advanced work. They have money for programs, so they say, okay, we're going to send a mission to Mercury. We have money for that. When you're in between, it's very hard to get a lot of money. So that's where private funding can come in. Besides having very obvious terrestrial benefits, there are military benefits to this. There's also a lot of potential to expand science. So people who are interested may want to bring in private funding. The problem is a lot of private funding is tied to very short-term capital returns, which we do not promise. You're talking about 5 years to get to fusion, but another 5 to 6 years to make a prototype before you can actually sell it to, say, NASA for missions. But in terms of enabling new science, if you have technology like this, which makes science, you get a return on your science much more quickly for lower cost, it'll enable a lot more private science than if you have to sit there and wait for a mission launch in 7 years and it has to go during this particular time, otherwise you have to wait another 7 years. If you're a scientist, what good does that do you? You know, you're getting your PhD, you design an experiment, and then 30 years later, you get results back. And that's what we're trying to do, is shorten that time span so that more science can be done. So it's more like going to Antarctica at worst than it is what it is now. Like New Horizons, 9 years before data came back. But they did stuff in transit, which was great. But if you were a Pluto scientist, you had to wait 9 years for that data, and you had to wait for all the data to be transmitted back, and you only got a little bit of data. So that's what we're trying to do, is make it more accessible. It's like accessibility to space with lower cost launchers. Same thing. You can do more. You get people into space and get more people involved than you can right now.
Yes, please.
I guess I'm going to ask a dumb question. This is really interesting stuff you just showed here. I guess I'm curious, why haven't other space agencies, or maybe they have, why haven't they pursued this technology? Are you the only one doing it?
There are, for example, there's a company, MSNW has an idea for a lithium liner fusion reactor for rocket propulsion, where you use a DT reaction and the neutrons are absorbed by a layer of lithium. They have NIAC phase 1, phase 2. It's one of those things where, because fusion, quite frankly, had such a bad name because of the length of time it's taken to get to the point where it may become practical. If you weren't around in the 50s. In the 50s, stellarators, fusion by 1958. Nothing happened. And then what happened was the Russians invented the tokamak. All of a sudden, we can get fusion power. Fusion power has been produced. But the tokamak path is $100 billion of investment before you get it. So NASA and other people interested in this kind of technology say, well, it's 100 years away. And it's only recently, through the work of pretty much small businesses, that NASA has gotten confidence that it can be done. And that's why they're funded. We have 3 NASA grants. We won 2 STTRs. We're actually developing subsystem components, the RF drive and the coils, because NASA says, you got to develop these technologies. And it's because they have, through our NIAC work and work done by other researchers, they've said, now we're thinking that it is possible to do fusion on a much smaller scale. NASA has no need for 1 gigawatt tokamaks in space, even if you could launch one. But they have a need for 1 to 10 megawatts for a variety of applications. Yes?
I mean, I guess when when I was thinking of spacecraft, as testing abilities, I mean, you think of a rocket or, a solid fuel or whatnot, I mean, you would scale up. I mean, how would you propose, what's the path to prototype that would convince NASA or some other funding organizations to, say that they invest money to get up something that can send Pluto?
Well,
how big or how small do you make this and
the engine itself, a 1 megawatt engine would be about the size of this. So it's quite small. That's, as I showed you the picture, that was about the size of the Hubble Space Telescope. As I said, we're limited in one engine to 10 megawatts. If you wanted to, say, send human beings to Mars, you might put together 5 of these or 6 of these, much like the Russians did with their launch vehicles. They had lots of little engines, not the big ones that we developed in the United States. So the engine itself is never going to go beyond 10 megawatts. You have to put them together in parallel. But that's good for redundancy. There are a lot of reasons you want to do that rather than have one big engine. But if you wanted to move a 1,000 metric ton space habitat into Mars orbit, this may not be the technology you would use. But for most robotic missions, this is ideal. As we showed, that we've done a lot of mission analyses, and this power range even from 700 kilowatts all the way up to 10 megawatts pretty much spans a lot of science and a lot of human missions that we'd like to do.
Thank you very much. This was very interesting.
Thank you.